is the slope of the inverse slope, okay? So let's get that taken care of first, and we'll start this way. I'm going to go this way. The function f, f inverse of x like this, what is that equal to? Always. This is a function times its inverse. What is that going to be equal to? If I ran it through this little machine,
Equal to x.
yes, it's going to be equal to x. Any questions about that? Okay? Now, the next thing I'm going to do is I'm going to make f, oh, this is supposed to be a little 1 here. F inverse of x, I'm going to make that equal to g at x. You'll see why in a moment. It just cleans things up and it brings you to something you already know. Okay? Now, what's the derivative of this? And it's just simply this. On this side, I'm going to go g prime at x. And on this side, I'm going to go f inverse bracket prime x. Is that all right? Just so you see that you've got this going and you have the prime for the derivative. Any questions on that? Okay, now, I've got this. I'm going to change this function now to be f at g at x.
Is this a proof?
Yes, it is a proof, but I'm not going to be holding you responsible for this one. Okay? Just follow me along on it. Okay? At this point, it's just preliminary work, and we're going to finish this thing off very fast. Any questions about what I have here? F inverse and all the way to x. Now I'm going to try to find the derivative of both sides. Chain rule. Although, what's the derivative of this?
1.
1. What's the derivative of this? F prime g at x
Times g prime.
times g prime of x. Right? Okay, now, I'm going to divide both sides by this. G prime of x, like this, and g prime of x like that. And so I have here f prime of g at x, like this, is equal to 1 over g prime of x. But we said this here happens to be equal to 1 over, see from what I have here, that's f inverse prime of x. The derivative of the inverse.
You folks a little bit.
And now I could go back here. No, do I want to do that? I could leave it this way, but I could go back now and put this back here like f prime of f inverse of x like this. Isn't that pretty clever? I showed you 2 examples of that as we were going along when I did the inverse. And so that gives you the idea. Now, let's do this problem that he had in the book.
Can you focus it?
Oh, yes. Okay. Let's do this function. F at x equals square root of x plus x squared plus 1. Now, I'm mainly doing this one because we want to take a look at this. What is the derivative of this? Okay? And what I'm really wanting here is what is the derivative of this quantity like this? And what I have here, and let me just, I have this function, so this is what I'm looking for. Prime of x. What does that equals?
1.
Okay, one other thing that we have here going, and that is we're going to do this at this point 1 comma 3. That's the point on this function that I'm looking for. So what this turns out to be is this, f inverse derivative of 3. Because this is an inverse of this one, so the orders get changed. Okay? Now, so I'm going to take this one, which I can do pretty easily. F prime of x is equal to 1 over 2 times the square root of x plus 2x. Any questions about this one? Have you done enough of them that you know what that is?
Yeah.
Okay?
You can write it another way, can you?
Okay. Otherwise, what we have up here is x to the 1/2, like this, equals y. Y prime equals 1/2 x to the negative 1/2.
Okay. Yeah.
Okay, so that's here. Now, what I'm going to do here, and this is where I tripped up a little bit last week. This is a 1 on this one here, is equal to 1 over 2 plus 2, which equals 5/2. So this one is 2 over 5 like that. Question on that? And you had to do 2 or 3 problems like this.
How do you know when to switch it?
Yeah, you noticed I stumbled over it, so I think I have an answer for it, somewhat decent.
Okay.
This one, you have to go straight forward and keep everything like it is. Okay? Now, when I do the inverse, as I'm thinking along, the x's and the y's get shifted for the inverse function because we're changing it over the xy axis. So the point I'm looking for here is 3,1, not 1,3. So I don't have to do anything about keeping anything straight, in a sense.
So on this left side, you just.
This
you
here?
can't do yeah, you can't do anything with an inverse, so you don't flip anything. And on that side, you flip it.
Yeah. And as if you start looking at the discussion in the book too, you can see that this was a y sub 0, I think, in the expression.
Yeah. So the
See.
bottom line there on each side, there,
This is the derivative of this one
yeah.
at this point, and this is the derivative of its inverse.
But now on the left side, the bottom line there, if you put f inverse of f prime at 1, then you get 2 over 5.
And I just take this number and plop it over here.
Huh?
Did I do nothing, just flip it.
Right, but if you wrote f inverse of f prime at 1, you would get 2/3.
You would get the wrong answer.
Why?
Because it's not at 1, it's at 3.
Oh,
Because in the book, when you get over here, there is a y sub 0. Let's go look at it. And this is x sub 0, y sub 0. Take a look at that. Yeah, bottom of page 207.
so you could do that right away instead of finding f prime at 1. You could just,
Oh, I didn't follow you. What you could have done here is found the inverse of this function.
yeah.
But that is not easy.
No.
That's terrible.
But what I'm saying is you could have just skipped to finding f inverse prime at 3 instead of doing f prime at 1.
You could have, yes.
Yes.
But then you gotta change the function over here. You gotta change this function over. Not this function, its inverse. And if you're gonna do it that way, then this here has to be x equals y, square root of y, plus y squared plus 1. And then you solve that for y.
Why would you do that though? You already know all the parts you need to just. Because you know f prime and you know your x and y points. And that's all you need.
I didn't follow that.
Well, you already know your f prime, you know x and y. So to find the first derivative of the inverse,
But just because you have the derivative of the first function doesn't automatically give me the derivative of the second function. I'm going to go on for a little bit. do some other things. Okay, we can come back at this tomorrow, you, to finish these problems, yes?
Can you do like one from the assignment?
Tomorrow.
What? They're not gonna be
What if
tomorrow.
you're gone?
Okay, we're going to YouTube it. We'll YouTube it again if you need that. And a number of you, who's not going to be here tomorrow? Okay, who's not going to be here Wednesday and Thursday? Okay, okay.
Can tomorrow just go to City Hall?
No. Tomorrow we will go over that kind of stuff. And I'll try not to go into too much new stuff. Okay, today we have to get some terms down and a few applications. So the first thing we're going to do is talk about a maximum value on an interval. Okay, and what we're going to do is I'm going to pick an interval like this, and this is going to be A, this is going to be B. And my function, we'll just take a nice little function like this, running from here. This one goes a little bit too far, it shouldn't be on here. Okay, now, watch what I have. In this interval here, this point is going to be the absolute maximum. Okay? Or global maximum. And this is how it's defined. This is the definition. Let f be defined on the interval. So this is I, from A to B, and it's a closed interval. And within this interval, there is a little point C right here. Okay? That's what it says here. A contains C. If we have this situation, f of C is bigger than or equal to any f at x, where x is all the other, any point in between here could be an x. Okay? For every x in here. This is the x-axis, so we're going to pick up all these little x's to produce this curve like this. And if this one is larger or equal to all of the other ones in here, then this is a max. And the minimum is very simple. This is a maximum, and it's a global or absolute. And if f at x is, or I don't want to do this, as it should be an f of c, is less than or equal to f at x, then it's a minimum, an absolute minimum. Okay? Not terribly tough stuff. Okay? Yes?
You need to zoom in again.
Focus it some more.
Tell me, Bob.
It's very low.
I'm just going to take this off, and we'll see what we need at the top in a few minutes. Okay, now, page 224, I think you can follow through there pretty easily. Top of page 225, there's a theorem. 225, a theorem. Before we get into it, look on the left, and it says this: the proof of the extreme value theorem relies on some deep properties of real numbers found in advanced books. Yeah, that's for people who love mathematics and keep working in it, Derek. Now, this is a theorem. What does this theorem say? The function that is contained in a closed interval, AB, has an absolute max and an absolute min. Okay? So if we have a function, it has to be continuous. It has to be continuous. And it will have an absolute max and it will have an absolute min. On the previous page, you just have worked through, you've read that, where there are some absolutes and some not. But the theorem says if it's continuous, you will have one of each. Okay? Any questions? There's an example that he talks about there, and you can deal with it. I don't think that is too tough reading. Okay? The next one at the bottom. We're going to shift from absolutes to locals. Okay? And by the way, this top one was the extreme value theorem. Kind of important to know the name for that one. Okay, then we do these locals. Okay? And at the bottom of the page, he has a nice little function that goes like this, and then he goes a sharp point like this. Okay, now, here's my function going along. this is a relative maximum. A short interval, and we have a max. Here is a relative minimum. This is a relative maximum. Okay? Now, the difference between this look and this look is can't find a derivative here. Because the derivative on this side has a slope this way, and the derivative on this side is different, and they have to be the same. Otherwise, it's not a derivative. Okay? So that's an undefined first derivative. So the first derivative here does not exist. F prime at, we'll just call this point D, does not exist. That does not exist. Yes?
So how do you know if it's local or relative or global?
Okay. Now, in this function right over here, we'll call this A, and we'll call this up to this point D, or B. Okay? Now, that's, if I, on this closed interval, A, B, like this, what is the max, the global or absolute? This is the highest point. Okay? Now, if I would like to call this point over here, I'm just going to go E. I don't want to go to C yet. Okay, now in between this interval, now this is going to be an open interval from A to E, like that. This interval.
Then it'd be
that point right here, which we'll call F.
Alright.
Okay? That's for shorter little pieces as we're going along. Okay? Now, on the definition on the next page, top of the next page, you get this here, and you're going to notice this terminology versus this. It says, suppose I is an interval on which F is defined, and C is an interior point. Okay? And it says it's an interior point, it's not an end point. Not all books write it this way. Okay? I'm not used to using the word interior point, but it works fine. It's in this open interval here. So we can't talk about the endpoints, but everything in between. And then you have this, what he says, f at C is greater than f of x for all the points in this interval, then that's a max. And if we go from C to D, or E, from E to D, like this interval, then that's a minimum. A relative minimum or a local minimum. Relative and local are the two words operative, and this book uses local. Okay? Okay, now, below that definition up there, he says, note, the local max and mins occur in interior points of an interval of interest, not at the endpoints. That's kind of important to know. Okay? Now, below that, you find the term critical points. We're going to want to know those, and he defines that at the bottom of the page. It's a definition again. An interior point C of the domain of F at which F prime at C equals 0. First derivative equals 0. Okay? Now notice what happens here. This is a critical point. The first derivative is equal to 0. This one also. That's a critical point. This one is also, which is the next part. It says here, or fails to exist. These are the critical points. So this interval here has a critical point here, here, and here. And you're going to want to deal with those. They determine lots of nice stuff. Okay? Now, right above that, it's a local extreme point theorem. Okay? And it says this. Now, before we go there, let's just go to the left again. And Fermat is attributed this to it, and it says this one. Often this theorem is attributed to Fermat, is one of the clearest examples in mathematics of a necessary but not sufficient condition. Are you logically literate with those words? The idea of necessary and sufficient? Okay? And it says here, a local minimum or maximum at C necessarily implies a critical point at C, but a critical point is not sufficient to imply that it's a local max or min. Okay? Example. Here's the example of this thing. I'm going to, let's see, I have to go How do I want to do this? I'm going to go this way.
Can you draw it on top?
Yeah.
It's too fuzzy down there. Okay. I'm thinking of how do I want to draw this thing yet. I'm going to go. Okay, I'm trying to depict that I go flat there for just a moment. Okay? It's shifting from this, probably, no, maybe I can draw a little bit even bit better here. We go like this, and then I start going this way. Okay? And right here, you see something happening, and I'm shifting from concave down to concave up, and at this point right here, it goes flat. Okay? And now that does not make that a max or a min, local, okay? And so, this is another one of those little trick questions dealing with tests and calculus, especially on exam kinds of times. Below that theorem 4, it says local extremes can also occur at points C where f at C does not exist. And we saw that a while ago on what I had done previously. So look at that stuff carefully. And also at the top of page 227, you have a local min at C where it does not exist. But that's not a continuous function. A, that's not a continuous function. And C, it doesn't because that has a sharp point, doesn't have a first derivative. So look over carefully that material. Okay? Now, the next thing we have to do is to find some of these things. So, how is that done? Top of the page. 229. Three things to do there. It says first, locate the critical points. Okay? So you do that. Evaluate F at the critical points and the endpoints. And then the all difficult thing is just look at the answers you've got, and the biggest one is the max, and the littlest one is the min. And you're going to have one if it's continuous. See? Now notice very carefully at the top of that procedure thing, it says the function is continuous. Okay? So, we will start with that first one there, because that's a rather easy one for today, and then we can get it finished before the end of the class period. We have here x to the 4th minus 2x to the 3rd. Okay, first off, I'm going to find, okay, it also says here, which is also pretty important, a minus 2 to 2, like that. Okay, my first endpoint is f at 2, and that value is going to be equal to
0.
Is it 0? 8. Okay, that's going to be a 0. Then we go f at a minus 2, and that's going to give me 16 plus 16 again. So that's 32. Okay?
Negative 33
Pardon?
and negative 34.
No.
Okay? So we're okay there. Now, next thing I'm going to take is the first derivative, and that's going to equal
4x.
yeah, see, now this is kind of easy in terms of what this one turns out to be. Okay, now I want to have this equal to 0 for my, because I know those are the points that are candidates for local minimums or absolute minimums and maximums. Okay, so I'm going to make that equal to 0. So I have here 2x squared times 2x minus 3 equals 0. And so in this case, I have x equals 0 and x equals 3/2, right? Now I've got to figure out those values. What is f of 0? Not f prime of 0. What is f of 0?
0.
0. Okay? So I got those two. That's interesting. It'll come into play in the answer in a minute. And then I'm going to go f at 3/2. And so that equals 81/16 minus 2 times 27 eighths
Negative 27/16.
equals negative 27 sixteenths, says DeVries. Okay, yes,
Where did you get 3 halves?
Next.
solving for this. 2x minus 3 equals 0. 2x equals 3. X equals 3 halves. Okay? Got it? Okay, now, all you do is look at what's the largest number? That's that one. So that's the max. And this one is the smallest, so that's the min. Okay? Now,
Wait.
the next thing I'd like to do is, oh, you have a question, Jeff?
No.
Okay, now, don't, you see what the assignment is up there, and it's due Wednesday. Don't wait until Tuesday night and start working on it. That's not the idea of this thing. I'd like to take a look at problem 20. 19 is up there, yes.
So you said you could, it wouldn't be a max if it was like the endpoint of a function.
Okay, would you ask that question and everybody listen to it?
Well, you said it wasn't including the like endpoint of a function.
Okay, yes, I did say that, but now, that's why you have to watch the language. What was I saying we couldn't use the endpoints? And the word was local,
Local? Oh.
the local ones,
Okay.
or the relative ones. Okay? Now, that is on page 226. Okay, see, that's what we're doing in between. Anything else on that? So now, in order to do this one, it happens at critical points or endpoints. Okay? So, you've read that section, you might want to read it again and pick up some things there that you need. Now, let's take a look at, I've asked you to do a number of these problems like 19. Let's take a look at 20 and see what he's trying to tell us there. He says this, we have f prime at x equals 0 at 1, 2, and 3. Okay? Now, also here, in this problem, we find the interval we're talking about is from 0 to 4. See that? And now we're going to sketch a graph. I think you guys have a fair grasp of some of this stuff, but let's just find out for sure. Here's 1, here's 2, here's 3, here's 4. That's the interval. And now, it says all of them are horizontal. The functions are all horizontal, and I'll just do it like this. No, not here. Okay? It's horizontal here. These are my little notes for drawing it. And at this point, I will put them all up here so they're not in my way. You can't always do this in a problem, but this is the way I'm going to do it. Okay? It has an absolute minimum at 1. Okay? And so this is going to be a minimum, like this. And I'll just put a big M here, meaning it's an absolute minimum. Okay? F has no local maximums. Okay? It says it does not have, F has no local maximum at 2. So that's not there. And F has an absolute, and this is not a local one. This is not a local one. We'll keep that in mind. And then it says F has an absolute one at, and it's a maximum at 3. Okay? And so this is going to be a max, and I'll just put a little M there. I know those are maximums. Okay, now, when I go through this point, I'm going to have to be flat. This is not going to be flat, and this is going to be flat. And this cannot be the maximum point, and this one cannot be the minimum point. Okay? So, I'm going to start here, and I'm just going to go down here like that. Okay? Now, that has to be the lowest point on my curve. And now this one has to be 0, and it's like what I drew a while ago. I'm going to have to draw something like this. I'm going to go up like this, and then I'm going to curve like this. Or maybe I should do it a little sharper so you can see it happen. Okay? No, that's not very good. That's worse. I like this curve better. Okay, this is the one I've got. Okay, so I'm going to go up a little, and then this way, and then up more. Okay, now this is going to have to be a max, so I'll go a little higher for the max there, and then I can come down here. Okay, now this isn't the only curve you could have. Now let's see if I've done my job. This has to be the max. This is min. This is 0, that's 0, and you see a 0 there too. Okay?
Maybe you're listening then.
Okay.